Hi, I'm Jun Wei, and my final year project is World Model with PSR Components, supervised by Assistant Professor Genevieve Rabinovic. This is the world model. It consists of three components. First, the visual component V model acts as the agent's eye. The agent observes a raw 2D image of the virtual environment, which has many pixels. However, it is difficult to train the agent to predict an entire observation frame. So the V model has to learn to compress the frames to lower dimension data called latent vectors without losing the essential information. To do this, a variational autoencoder is used. The second component is the internal model. This model gives the agent its predictive capability, which uses historical data to predict the future. In the original world model, mixture density network or MDN is used. MDNs are neural networks that parameterize a mixture density distribution. This is required when the target variable does not follow any single parametric distribution. In this study, predictive state representations or PSR is used. PSR is based on the prediction of tests, which are finite sequences of action observations. The third component is the agent's policy, which tells the agent the best action to take given the current observation and predicted future to optimize the reward received during the rollout of the environment. To effectively compare the performance of the two internal models, I opted to use the same controller in the original world model, which is just a simple linear neural network. For easy reference, I will call the VAE V model, the two internal models MDN is M model, and PSR is P model. The C model is a linear controller. The agent with PSR is P agent, and the agent with MDN is M agent. For the experiments, the steps are as follows. First, I initialize the random agent. Next, I record observation frames by collecting 1000 random rollouts of the environment. Then, I train the V models to encode the observation frames on different sizes of latent space, namely 4, 8, 16, and 32. Then I preprocess the observation frames into their latent vectors. After that, I train the P models with these preprocessed frames and pick the best P model for training of the C model. Finally, I train the C model on an equal CPU. In the car racing experiment, the agent needs to navigate a top-down car on randomly generated tracks. The final reward depends on how precise the car is and how long it took for the car to complete the circuit. In the Pong experiment, the agent plays the Atari game Pong. The goal is to deflect the ball back at the AI with the paddle. The agent not only needs to deflect the ball, but the ball needs to be deflected in a way that prevents the AI paddle from receiving the ball. For the results, in car racing, the VAE loss of the different latent spaces are similar, meaning that the V model can encode the observation frames to both small and large latent space as well. The decoded frames also retain most of the important information. This means that there are redundancies in the latent vectors of higher dimensionalities that may not be important for learning the agent policy. The PSR models trained on larger latent vectors could not learn, as seen from how the validation loss rises or the training loss only drops slightly. When the latent space is eventually reduced, the model starts to learn. When the latent space is of size 4, the learning converges quickly. So the P model trained on latent vectors of size 4 is chosen. The controller with the selected P model performed better than the controller with the existing M model. The rewards obtained by the P agent converged at a higher level and earlier than the M agent. For Pong, the VAE losses dropped sharply by the 20th epoch and converged in a fluctuating manner. Similar to car racing, the decoder frames of various latent space retain the important features. This means that the large latent vectors must have redundancies, which are not important for learning to perform the task. Similar to the training of P models in car racing, the P model here did not perform well with large latent vectors. When the latent size was 16 and 32, the P model did not seem to learn, resulting in high losses. When the latent vectors are smaller, the loss drops. Since the P model trained on latent vectors of size 4 has the best predictive capability, it is selected for training the C model. Since there is no pre-trained M model for this environment, I trained the M model from scratch. Similar to the P model, the M model seems to learn well on data with small latent sizes. So I selected the M model trained on latent vectors of size 4. During the training of the C model, the P agent generally obtains higher rewards than the M agent. However, both agents achieve very negative score, which means both agents were losing to the AI. From the results, it seems like the internal model performs better on smaller latent vectors, especially PSR. Hence, in the car racing environment, I also applied various P agents trained on different latent vectors. In the beginning, all three agents have comparable scores. After the 50th epoch, the P agent trained on latent vector of size 4 outperformed the other agents. This is expected since the P model was shown to have the best predictive capability. To verify that a smaller latent space gives better results, I also trained an M agent on latent vectors of size 4. The graph shows that the internal model trained on smaller latent vectors gives better rewards. It also shows that towards the end of the training, the M agent achieves similar results to the P agent for latent space of size 4. In this study, I have replaced the MDN model with the PSR model and showed that it can achieve better, if not comparable, performance on the car racing and Pong environments. I also found that reducing the size of the latent vectors improved the agent's performance. However, due to the CPU constraints, I was unable to train the C model well, which leads to the poor performance. So for future work, more CPU cores can be used to improve the performance. Thank you.